Hello, this is Dr. Keith Miller again, and this is part two of my videos on weather and climate change. So in this part, we're going to concentrate on uh, the relationship between increased global warming, impacts of current climate change on storm events. So let's look at thunderstorms. So we first take some time to understand how thunderstorms are formed. So thunderstorms have a life cycle. They have what's called a cumulus stage, which is rising air cools, rapidly rising air, again, air that is warmer and has more moisture in it is lighter and it will rise. And as that warm, moist air rises from the lower atmosphere upward, it starts to cool off. Eventually, it reaches the dew point, at which time condensation occurs and the water precipitates out of the atmosphere. So once the thunderstorm has built up into essentially to the top of the troposphere, the air is now cooled off enough that's below the dew point. Precipitation is happening, so that it's starting to rain out. And as that rain falls, it tends to pull this now cooler air back down to the surface again. So now we have both rising air as the warm, moist air rises, and then cooler downdrafts associated with the rain that's falling. Eventually, the updraft ends, the rising air ends, it dissipates, and the storm then just rains out. So here is an image of a thunderstorm in its cumulus stage. So it's early formation stage. So now we have this rapidly rising air. So you get these cumulus clouds that are rising, pushing up into the atmosphere. Water is condensing out, forming the clouds as that rises. Then eventually that rising tower of clouds can hit the top of the troposphere. And then what you see is the clouds form what's called an anvil, which is this flat top. So what you're seeing there is actually the top of the troposphere. This is now a fully mature thunderstorm. So you have rising air that's rising all the way to the top of the troposphere. It's cooling. The rain, precipitation is raining out and falling to the ground and bringing with it a downdraft. And then eventually the updraft ends and you just have rain and descending air. So that's the life cycle of a thunderstorm. There's a certain subset of thunderstorms called supercell thunderstorms. And in these, you have the same rising, moist, warm air, falling, cooler air within the storm. But the difference here is that those updrafts and downdrafts are rotating. So the rapidly rising air is rotating, and often very quickly. Where that intense updraft is where you can have a tornado. And then the descending air also rotates, but more slowly. So you have something that looks like this. So you have the rising air being pulled into essentially this local low pressure, being pulled into the storm. And then as it does so, it starts spinning and rotating upward. Cools off, hits the top of the troposphere, and then falls down. And then you have the sinking air pictured there on the left, which then also rotates, so some of that air is actually pulled back into the updraft again. So here's an actual picture, very spectacular. On the left-hand side or central part of that image, you're seeing a part of the cloud which seems to be lower than the rest, that's the rotating updraft. And on the right-hand side, you see that kind of yellowish area there. That's the rain out part. That's the downdraft. So you can see both the downdraft and the updraft. And again, if a tornado is going to form, it's going to form in that intense updraft, which we call a wall cloud. That lowered base to the cloud is called a wall cloud, and that's an indication that it's rotating and that tornado formation is likely. So how does global warming, how does climate change impact this? The warmer the rising air, the more moisture that air can hold. So we've talked about that in part one. So since the air is holding more moisture, when it hits the dew point, it's going to increase the amount of rainfall. So with increasing warming of the globe, rainfall events will become more intense and longer. And heavy rain can cause a multitude of potential hazards. You have flash floods, particularly with supercell thunderstorm kind of floods, very intense, heavy rainfalls in a very localized area. That can cause landslides. You can have crop damage. And this is aside from the impacts of tornadoes. So again, the more moisture that the air holds, the more moisture is there to rain out during a rain event. And this is a diagram from NOAA, and it's a projection about the intensity of rainfall events moving into the future. And the way rainfall events are categorized is by saying that this was a 50-year rainfall or a 50-year flood or a 100-year flood or a 20-year flood, which means, say, a 20-year flood is something that on average, doesn't happen every 20 years, but on average over a long period of time, you would have an event of that intensity about every 20 years. Okay, a 100-year flood or rainfall would be something that you would only expect one time in a 100-year period, again, over an extended period of time. And what this shows is that over a large portion of the year, it's looking at how frequently would what's now considered a 1 in 100-year storm, how frequently is it likely to occur in the future. And what you see is that they are likely to occur much more frequently. So a 100-year flood, the darkest there says that a 100-year flood will now occur in every 10 years instead of every 100 years. So this is an indication of an impact of increasing global temperatures because of increased capacity to hold water is going to increase the frequency of what we consider significant flooding hazards. So what about tornadoes? Tornadoes, again, are produced by supercell thunderstorms within the rotating updraft part of the storm. And again, out of what we call a wall cloud, which is a lowered cloud base from the rapidly rising air in that part of the storm. So here are some spectacular examples of wall clouds. Very much an indicator of a high tornado risk. what we think of as a tornado uh, is a funnel cloud. And it really is a cloud. The reason you can see a tornado, or usually see a tornado, is that the pressure drop is very high. So there's a very rapid drop of pressure within the tornado, within that rapidly rising air. When you lower the pressure of something, it gets colder. So the more rapidly the pressure drops within the rising air, the colder it is. And if it's cold enough, it hits the dew point and water condenses out. So in a tornado, what you're actually seeing is that very rapidly rising air that's cooling off so quickly that it immediately condenses out. So you can see it. Interestingly enough, in tornadoes where the pressure drop is not as great, they're actually invisible. The only way you would see a tornado is when it picks up dirt or debris and makes it visible. But what we think of as a funnel cloud is a factor of the air rising, rapidly rising, depressurizing, temperature dropping, and hitting the dew point. Tornadoes are highly variable in size and destructive power, from very weak tornadoes that are only several yards across to ones that are over a mile across. So here's kind of a typical looking large tornado with a very prominent funnel cloud. This is a very large tornado, what are called wedge tornadoes. These can have some of the most extreme cases of damage. And some, especially wedge-type tornadoes, can actually have multiple vortices that are actually rotating around each other inside of the larger wedge tornado. And these can be particularly destructive. Tornadoes are classified by what's called an EF scale. And the higher the wind speeds within the tornado, the higher the EF value. So an EF 0 is between 65 and 86 and so forth. So you have EF 0, EF 1, EF 2, EF 3s, EF 4s, and the most intense are EF 5s. Each of the images show what they would look like. So EF 5s are so intense that except for extremely sturdy structures, they're going to be completely swept off their foundations. So all you see are concrete slabs, for example. So again, how does current climate change impact tornadoes? It's unclear whether the frequency of tornadoes increases. That's really not something that is agreed upon at all by the weather and climate studies that have been done, long-term studies. But one thing that does appear to be happening as a consequence of climate change, of global warming, is that the location of the most intense and most frequent tornadoes is shifting. Tornado Alley used to be right up the center of the US, so right from like Texas to the Dakotas. So that's where the most intense tornadoes were, the most common tornado occurrences were in that strip. What we're finding now is that that has moved eastward. And so now the most intense tornadoes, the most common tornado activity is further to the east, up the Mississippi Valley. And we've seen this actually just in recent storm events this year. All the major, uh, most of the major tornado occurrences and destruction has been in that red band, not the typical band up the center of the country. So again, it's an impact of current climate change. Another type of storm that we can look at are called mid-latitude cyclones. Cyclone just means that you have a circulating storm. Mid-latitude cyclones are very large storm systems. And because they're based on low pressure systems, they rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. And they're large enough that they're impacting a very broad geographic area. And typically what they do is you have a mid-latitude cyclone going through the US, for example. They're going to be rotating counterclockwise, which means that it's pulling air down from the north on the west side of the storm. It's pulling cooler air down and then pulling warmer air up from the south. And the result is you get trailing warm and cold fronts. So you typically have a warm front out in front of the moving cyclone that's pulling warmer air up from the south. And then you have a cold front behind it on the west side of the storm, result of pulling cold air down into the warmer air. And these, particularly the strong cold fronts, if you have very warm air in front of it, can produce very strong thunderstorms. Oftentimes you have big tornado outbreaks or supercell storm outbreaks along that cold front. So one thing you might expect in a warming world is because that warmer air is warmer out in front, holding more moisture, you're going to have more intense thunderstorm activity. So here is a illustration with the standard weather symbols. So you have the blue cold front that's pulling the cold air down from Canada into North America. And then on the right side, you have warm air coming up from the Gulf and pushing into Canada. And the whole system is rotating around that low pressure system. And the cold front itself looks something like this in cross section. So you have the cold air. This cold air is going to be drier and colder. It's going to be dense. So it's going to be hugging the ground. So as that cold front's pushing in this case from left to right, it's pushing underneath the warm air that's out in front of it and causing that warm air to push up higher in the atmosphere. So now you have this warm, moist air that's being forced upward by the cold air pushing into it. As it rises, it's going to cool, it's going to hit the dew point, and it's going to precipitate out. And so you're going to build up thunderstorms as that warm air is being lifted in front of the cold front. So here's a classic looking mid-latitude cyclone. This, in fact, was the strongest mid-latitude cyclone on record in 2010. And you can see the beautiful counterclockwise rotation. The clear air behind it is that cold air that's pushing in. And then you see all those really brilliant white large clouds on the right side. Those are all supercell thunderstorms that are blowing up in front of that cold air that's pushing into the warm, moist air ahead of it. And this is a close-up of that. And this had one of the largest tornado outbreaks on record. So each of those blobs is a big supercell thunderstorm, and they almost all were forming tornadoes, some of them very long track tornadoes. and very powerful tornadoes. So lastly, the last type of storm I'm going to talk about are tropical cyclones that we call hurricanes. They're called different things in different parts of the world. We call them hurricanes, tropical storms and hurricanes. And again, they're centered around low pressure systems that draw in moisture-laden warm air. And they're forced into a spiral by the Coriolis effect. And if they have a sustained wind of more than 74 miles per hour, we call them a hurricane. So again, here is a classic looking hurricane. Again, it's rotating counterclockwise. It's pulling from the surface of the ocean. It's pulling in warm, moist air. Again, we'll be talking about this in a little, more in a couple later slides. As the surface of the Earth warms, that produces extra fuel for these storms. These storms are fed by warm ocean water. That's what drives them. They're driven by the evaporation of the oceans. So you have warm, moist air, and that warm, moist air is rising. And as it rises, it cools, hits a dew point, and precipitates out. One of the peculiar things about hurricanes, if you look at wind speeds, the wind speeds are greatest right near the center, what's called the eye. In a very powerful hurricane, the center of circulation is actually clear, clear of clouds. And the most intense winds are right around that cleared area. It's called the eye wall. And that's where the most intense winds are, the most intense rains, the most intense part of the hurricane is in that wall cloud and near the eye. A few things about the formation of tropical cyclones and hurricanes. They form in the tropics, but not at the equator. And that's because they need two things to fuel them. One is they need warm ocean water because they're evaporating that warm ocean water. That's where they get their energy. That's where all the energy comes from. It's from latent heat. But they don't form right at the equator. And the reason they don't form right at the equator is at the equator, there's no Coriolis effect. So it needs warm water for its energy, and it needs a Coriolis effect to spin it up. So again, it's energy. The energy that it powers it is from the evaporation of warm ocean water, and the Coriolis effect is what causes it to spin. So if you look at the temperatures, the warmer the oceans get, the more energy there is. Remember, I talked about oceans having a high heat capacity, which means that the ocean water stores a lot of heat energy. So if the water is very, very warm, the ocean water is very, very warm, there's a lot of heat energy stored there. And the more heat energy that's stored in the oceans, the greater the power of the hurricanes, greater the energy available to hurricanes and tropical storms. So this is looking at the Eastern Pacific, same thing. And these are each of those little threads of blue light, lines is a track of a hurricane over a period from 1985 to 2005. And notice there aren't any right at the equator, but north and south of the equator, and particularly in the northern hemisphere. Tropical storms and hurricanes are much more stronger and numerous in the northern hemisphere. And they have this very typical pattern because of the prevailing winds. They tend to start out as close to the equator as the Coriolis effect will allow them. And then they're blown by the prevailing winds from east to west. But then they drift north, and as they drift north, they're picked up by the westerlies in the mid-latitudes and then pulled from west to east. So they all have this kind of curve to them. So what's the climate impact on tropical cyclones? The main things we've observed is not really an increase in the number of events, the number of tropical storms and hurricanes, but in their rapid intensification. In other words, there are other conditions that are required to get a storm going. And that doesn't seem, at least now, doesn't seem to be being affected by current climate change. But since the oceans are so much warmer, when they do get going, they have a lot more energy and they tend to spin up much faster. So there's an increase in the proportion of high category storms. Also, more intense rainfalls are likely, again, because the air is holding more moisture. This results in problems of coastal flooding in the case of these storms when they make landfall, and also because they're more intense, they have higher winds, and this increases the severity of what are called storm surge events, which is water that's pushed up against the land, against the coast by the high winds. And again, I've shown this in my earlier part one of the increase in global ocean heat content. And again, this is directly powering these storms. That's where they get their energy from, is simply surface ocean temperatures. So this results in stronger storms and more rapid intensification. This was an example of Hurricane Helene from fairly recently. And it went from a Category 1 storm to a Category 4 hurricane within 24 hours, which is a very rapid intensification. So tropical storm hazards include heavy rains, heavier rains associated with slower moving storms. And, excuse me, they can affect areas hundreds of miles inland. This is an example from a number of years back in New York State from Hurricane Lee, well inland, but again, very intense rainfalls. Same with Hurricane Hannah. Well, in this case, not inland, but really intense storms in an island setting, Pacific Island. And then storm surge. Again, storm surge is the piling up of water against the shore at landfall. And this is primarily on the right side of a landfalling hurricane in the northern hemisphere, because in that case, the wind is blowing toward the shore. And really, storm surge is the greatest hazard of landfalling cyclones. This is from Hurricane Katrina. This damage is not from wind. This is from storm surge. So this is a coastal community, and this was destroyed by the intense rise of water at the coast combined with high waves. So these were destroyed by rising ocean water. Same about this. This is a hurricane that made landfall on the Texas coast. This was a barrier island in that area. And as you can see, it was completely stripped of all of its buildings, all the houses. You see those white slabs, those are where buildings used to be, with one remarkable building standing out that wasn't destroyed, although it did have water flowing through it, so its interior would have been messed up. And this had to do with what you can do with really good building construction.